So in this section we are going to discuss the most important concept in the differential calculus of complex variable functions. Okay, and that is what we call the concept of analyticity. Okay, now this concept apparently doesn't have any real counterpart. We have limits in both the real and the complex calculus. We have continuous functions and we also have differentiability, but analyticity is something wherein the complex variable calculus starts really deviating from the real counterpart. Okay, so we'll see what analytic functions are. Okay, and also we will introduce ourselves to the two very important partial differential equations which we call the Cauchy-Riemann equations. Okay, all right. So what is an analytic function? Suppose we consider any function f of z, okay, and we call it analytic in a domain D. And see, here we are using the word domain in the context of complex numbers. Okay, so domain D means D is both an open set and a connected set. Okay, so if we have such a set, we call it a domain, and we call f of z to be analytic in a domain D if two requirements. Requirement number one, it is defined everywhere inside D or at all points of D, and more importantly it is differentiable. Okay, now the first one may seem obvious, but and the second one does imply the first one. Okay, if it is differentiable then it has to be defined there. Okay, because f of z naught does appear in the difference quotient. Okay, and so this is the analyticity in a domain. How can we define analyticity at a point? Simple. So for analyticity at a point z naught, okay, let us say z naught is a fixed complex number in the domain D, it should be analytic in the neighborhood of z naught. Meaning if we consider a circular neighborhood, okay, surrounding z naught. Now although I have shown it with a thick boundary, okay, it is an open set. Okay, so in this neighborhood it should be differentiable. Only then we call it analytic. Some people call it holomorphic. Okay, but both these words are synonymous. If a function is analytic, it means the same thing as the function is holomorphic. Okay, now we also have a term known as entire function. Okay, now entire functions are those functions which are analytic throughout the entire set of complex numbers. Okay, and the best example is the complex exponential function e to the power z. Okay, we have already talked about this in our previous session. Okay, so for analytic function, for a function to be analytic at a point, it should be analytic in the neighborhood of z naught, meaning it should be defined and differentiable in the neighborhood of z naught. Okay, fine. Now two classic examples of analytic functions. We have already talked about one example, that is the complex exponential function. We have two more classes of analytic functions. First one is polynomials. Okay, so f of z, if it is in the form a naught plus a1z plus a2z squared so on till a n z to the power n, where all aj's belong to the set of complex numbers. These are called as polynomials in set. Okay, so all polynomials are analytic everywhere. We have already seen an example, that is z squared. Okay, and we have seen that its derivative is 2z. Secondly, and see, let me tell you that z bar is not a polynomial. Okay, Alright. Now rational functions are an extension of what we know as a rational function. Okay, so rational function f of z is a ratio of two polynomials in z. Now this is analytic everywhere except when the denominator is 0. Okay, so except for finitely many points where the, well, at zeros of the polynomial in the denominator, at all other points the rational functions are, or this rational function is analytic. Okay, fine. Now do we have any quicker method to establish the analyticity? Yes, that is what we call the Cauchy-Riemann equations. Okay, so these equations have been named after two mathematicians. Cauchy, I think, was a French mathematician, and Riemann was a German mathematician. And a very famous Riemann hypothesis is named after him because he was the first one who proposed it. So this is still an unsolved problem, and if you either prove this hypothesis or disprove it, you'll get $1 million. Okay, this is the prize offered by Clay Mathematics Institute. Okay, now it actually requires you to know the complex analysis, okay, or the calculus of complex variable functions. All right, so what are these equations? As I told you earlier, these are two partial differential equations. We have already studied ordinary differential equations. So in a partial differential equations, we have at least one derivative of a multivariable function. Okay, so what are they? Cauchy-Riemann equations are a criterion for the analyticity of f of z. Okay, and for a function to be analytic, these equations must be satisfied. Okay, equation number 1, partial derivative of the real part of the function must, with respect to x, must be equal to the partial derivative of the imaginary part of the function with respect to y. And equation number 2, partial derivative of the real part of the function with respect to y must be equal to minus partial derivative of the imaginary part of the function with respect to x. Okay, so ux equals vy, first one, and second one uy equals minus vx, this one. Okay, so if these equations are not satisfied, then the function is not analytic at that point, meaning it is not differentiable. And if the equations are satisfied, the function may be analytic. Okay, fine. So we have now the theorem. Okay, what does the theorem say? This theorem requires you to know continuity of multivariable functions or two variable functions, which we have already seen. Okay, so the theorem says that if u and v, which represent the real part and the imaginary part of our function, not the input variable but the output one, okay, and if these functions are continuous, have continuous first order partial derivatives, okay, and are such that the Cauchy-Riemann equations are satisfied in some domain D, then f of z is analytic in D. Now it is pretty much clear what requirements the function demands. Okay, satisfaction of the partial derivatives implies that the partial derivatives should exist first. Okay, and so if the functions are continuous and have continuous first order partial derivatives, we say that the Cauchy-Riemann equation, and if the Cauchy-Riemann equations are satisfied, then the function is analytic. Okay, now we also have polar form of the Cauchy-Riemann equations, which may be useful in some of the problems, not all of them, but some of the problems. Okay, so in the polar form, what we do is we don't express u and v as functions of x and y, but instead we make use of the polar coordinates r and theta. Okay, We have seen how to change the independent variables using partial differentiation chain rule. Okay, so suppose u and v are expressed in terms of r and theta, where r and theta have their usual meaning, and tan theta is y upon x. So there we have the Cauchy-Riemann equations in the polar form. Okay, and these equations are: equation 1, partial derivative of u with respect to r is 1 upon r partial derivative of v with respect to theta. Okay, and partial derivative of v with respect to r is minus 1 upon r partial derivative of u with respect to theta. Okay, now you may remember these two equations with the help of the dimensionality criterion. Okay, what is it? If you are differentiating u with respect to r, essentially you are multiplying the dimensions of u by L to the power minus 1, because r is length. Okay, and if on the right hand side, if you are differentiating v with respect to theta, essentially you are not changing the dimensions of v, meaning to match the dimensions of LHS and RHS, you must divide the RHS by r. Okay, same applies to the second one too. Okay, di by v by di by r is equal to minus 1 upon r di by u by di by theta. Okay, so we are actually going to solve one problem using the polar form of the Cauchy-Riemann equations. Okay, fine. Question 1 on Cauchy-Riemann equations. Show that the function f of z, which is square of the modulus, is differentiable only at z equal to 0, and hence it is nowhere analytic. Okay, see, now you may ask, if it is differentiable at z equal to 0, can we not say that it is analytic there? No. For this you need to understand the definition of analytic functions, where we said that the function has to be differentiable not only at that point but also in the neighborhood of the point. Okay, for analyticity at a point z0, it should be analytic not only at, well, it should be differentiable not only at z0 but also should be differentiable in the neighborhood. Okay, hence the question is correct. It is saying prove that it is nowhere analytic. Okay, very simple. We will go to f of z and try to express it in terms of x and y. We know what mod z is, which is r essentially, so x squared plus y squared. Okay, now because modulus is always real, we may safely assume that v is 0 in our usual notations. Yes, so and of course u is x squared plus y squared, the real part. Check for validity of Cauchy-Riemann equations. Now one thing is for sure, u and v being x squared plus y squared and 0 respectively, they are continuous everywhere. Okay, that is one good sign. Alright, so we can proceed. Find the partial derivatives of u with respect to u and v. With respect with respect to x and y, sorry. Find the partial derivatives of u with respect to x and y. With respect to x, you will get 2x. With respect to y, you will get 2y. Okay, now go to v and find the partial derivatives of v with respect to x and y. With respect to y as well as with respect to x, the partial derivatives will be 0, obviously, because v is a constant. Okay, now the functions that we have got here are such that they are continuous everywhere. Yes, so they must be continuous at origin, okay, or at 0 plus 0i. Okay, now let us see whether or where Cauchy-Riemann equations are satisfied. Okay, first pair is ux should be equal to vy. Okay, so when you equate 2x with respect to 0, you get x equal to 0. It means on the entire y-axis, the first Cauchy-Riemann equation is satisfied. However, what about the second one? Okay, u with respect to y equal to minus v with respect to x. The second one. Okay, for this 2y should be equated to 0 or you will get y equal to 0, which means the second Cauchy-Riemann equation is satisfied only for those points which lie on the real axis, okay, or on x-axis. which means the satisfaction of both of them takes place only at the origin. So what does this mean? This means that, okay, although Cauchy-Riemann equations are satisfied at the origin, okay, at origin, mod of z squared isn't analytic there, or in fact it isn't analytic everywhere, okay, simply because it is not differentiable in the neighborhood of the point 0 plus 0i. Okay, fine. So a pretty simple question. Now I will solve two more very typical questions based on Cauchy-Riemann equations. Okay, these are associated with the modulus and the amplitude of complex number. Okay, question 2. Show that an analytic function with constant modulus is constant. Okay, first let me explain what this problem is actually asking us to prove, and then we will go to the solution. Okay, point number 1. Okay, we have an analytic function, which means it satisfies the Cauchy-Riemann equations everywhere. Okay, at least in its domain. Secondly, we know that this function is such that its modulus is constant. It means, well, at this stage, no matter what values you put in for x and y, f of z's modulus is always going to come out to be the same thing. Okay, for instance, suppose the outputs which are produced are, let's say, 2 plus 3i, and the mod of this is root 30. Okay, and let us say something else produced the output root of 13 plus 0i. So again the output is root 13. Yes. Okay, but this problem is saying that if the function is analytic, okay, and if mod of f of z is constant, then you cannot get two different images. Okay, the function is always constant, so every complex number will get mapped to a single point. Okay, that is what this problem is actually asking us to show, and we will now take the help of the, well, many things, but primarily we will make use of the Cauchy-Riemann equations. Okay, so we'll start with assuming that the function w has the real part u. Excuse me, my laptop. Okay, we will start by assuming that the function w has real part u and imaginary part v. Okay, and what is given is this function produces outputs which have the same modulus. Okay, so mod of w, which is root of u squared plus v squared, it will be k. Yes, now the key point is you immediately square. So on squaring you will get rid of the root sign. Okay, so you will get the equation u squared plus v squared equal to k squared, I mean, which represent actually the concentric circles in the w plane centered at origin, but that's not important. Okay, fine. Now what we are going to do is we are going to apply the Cauchy-Riemann equations on this on u and v basically. Okay, for that we will differentiate our equation that we have with us, or both sides of the equation, with respect to x and with respect to y partially. Okay, so let us first do that for x. Okay, so differentiate both sides with respect to x. K squared's derivative will be 0. Derivative of u squared by chain rule is 2u da by u by da by x, derivative of v squared with respect to x will be 2v dab by v by dab x, again chain rule. Okay, at the same time let us also differentiate LHS and RHS with respect to y. Okay, now this is not going to produce any different results. Okay, similar results. A squared's derivative 0, u squared plus v squared's partial derivative with respect to y is 2u dab by u by dab by y plus 2v dab by v by dab by y. Okay, and now what we will do is the following. Okay, we will show that the real part is constant. That means we will show that u is constant. Now to show that u is constant, it is enough to establish that both dab by u by dab by x and dab by u by dab by y are 0. Yes. Okay, and to show this, what we will do is excuse me, we will eliminate everything that has v in it. Okay, now there are two such things. First is we have dab by v by dab by x here, and secondly we have dab by v by dab by y here. Now the elimination requires us to make use of the Cauchy-Riemann equations. Okay, so I'll say by Cauchy-Riemann equations, replace dab by v by dab by x by minus dab by u by dab by y. Okay, yes, and replace dab by v by dab by y by dab by u by dab by x. Okay, now this has successfully led us to two partial differential equations involving the same unknown function or same function u. Okay, u dab by u by dab by x minus v dab by u by dab by y equal to 0, and u dab by u by dab by y plus v dab by u by dab by x. Although we have not yet eliminated v, okay, we have successfully eliminated the partial derivatives of v, right? And later on you will see that we also have this equation with us, okay, which will help us in even eliminating v or replacing u squared plus v squared by a constant. Okay, all right, so now what I'll do is I will square both these equations and adding, we'll get the following result. Okay, RHS of both these equations will be 0, so RHS of the resulting equation will also be 0. Okay, now carefully observe the result. When you square the left hand side of the first equation, you're going to get u squared dab by u by dab by x squared plus v squared dab by u by dab by y squared minus 2 times uv into ux uy. Okay, and when you square the left hand side of the second equation, what you will get is u squared dab by u by dab by y squared plus v squared dab by u by dab by x squared. Okay, however, now you will get plus 2uv ux uy. Okay, and when you add them, this leads to the cancellation of these two terms, right? Yes, and because we have successfully cancelled them, it actually allows us to take u squared common and v squared common, and it will then allow us to factorize this, which then boils down to u squared plus v squared multiplied by dab by u by dab by x squared plus dab by u by dab by y squared. Okay, now this equation is extremely important as far as our objective is concerned. Okay, because this equation has product of two functions, I would say, or two terms, okay, and which is equal to 0, and we know that the first term is u squared plus v squared, and this term is always going to be I would say non-negative. Well, okay, it can be anything, but well, it has to be non-negative because both u and v are essentially functions of real variables x and y. Okay, so let us consider two possibilities. If both u and v are 0, only then the function is only then this product will be 0. However, if both of them are 0, then u plus iv will be 0, and this automatically proves that the function is constant. So let us consider a non-trivial case wherein both u and v are not 0 for all values of x and y. Okay, this means the first term cannot be 0. So clearly that forces us to take the second term to 0. And because again we have a product of partial derivative, again we have squares of I would say real numbers, okay, real numbers, dy by dy x and dy by dy by y, and we are more importantly adding them, which means both of them must be 0 individually. Yes, so if dy by x is 0, the definition of u cannot contain x, and if dy by y is 0, then the definition of u cannot contain y, which implies that u is a constant. Okay, yes, and so we have successfully managed to show that at least the real part of the function must be constant if it has constant modulus. Okay, and now our job is to prove that the imaginary part is constant too, and for this you need to eliminate, I shouldn't say you, I should say eliminate partial derivatives containing u, and follow a similar strategy which we have followed for v. Okay, so that will give you two partial derivatives of v with respect to x and y. I mean, the result itself will hint you that both of them must be 0. So that proves the result that if we have an analytic function which has constant modulus, it has to be constant. Okay, see, now this result applies only for analytic functions. If the function is not analytic, then the function need not be constant, and the best example is this. Okay, suppose we consider a function which is defined only for 0 and 1. Okay, 0 is mapped to 2 plus 3i and 1 is mapped to root 13 plus 0i. The function is defined only at these 2 points, so it is not differentiable anywhere, and that is enough. Okay, fine. So we have now dealt with constant modulus question. Let's now solve a similar question wherein we will have analytic function with constant amplitude, okay, or argument. Okay, question 3. Show that an analytic function which has constant amplitude is constant. Okay, again we should write down carefully what we have, okay, to understand the problem better. We have an analytic function, okay, and this function is such that the argument of w is constant. Meaning, for all values of x plus iy in the domain of the function, okay, whatever w value you are getting, its argument is always constant. Okay, but the problem is saying that you cannot have two distinct w values. Okay, it must be the same. Okay, that is the meaning of the function being a constant. Okay, see, that means you can define a function, let's say at 0 and at 1, only at these 2 points. Okay, and you'll say let's take f of 0 as 1 plus I, and let's take f of 1 as 2 plus 2i. So for both of these complex numbers, the argument is pi by 4, the principal argument. Yes. Okay, let's call it w straight away. Okay, constant amplitude, but the function is not constant, and at the same time it is also not analytic because it is defined only at 0 and 1. Okay, so once we understand what we actually are supposed to prove, we can start solving the problem. Okay, step 1, introduce u and v, because the moment you know that the function is analytic, we have to introduce the Cauchy-Riemann equation somehow. Okay, all right, usual notations. Let w be f of z or u plus iv, u the real part of w, v be the imaginary part. Okay, now what do we mean by constant amplitude? Okay, first of all, let us write down the amplitude of w, which is tan inverse of v upon u, and if this is constant, Again, v upon u has to be constant because it is tan of a constant entity. Okay, now you should take some caution here. Do not shift u to RHS. Okay, you can see it for yourself what happens when you shift u there. Okay, see, the main thing is we don't want this k to appear in our calculations, and the best way to do that is keep it on one side and differentiate. You will get 0 on the right hand side, and hence k will automatically get eliminated. Alright, now differentiate both sides with respect to x and with respect to y. Okay, and see what happens. Apply the division rule. Derivative of the first function, second function as it is, minus first function as it is into derivative of the second, divided by square of the denominator equal to 0. Okay, and same thing you can do for the partial derivatives with respect to y. Dabba v by dabba y into u minus v into dabba u by dabba y upon u squared equal to 0. You can now shift u squared to the other side. Okay, so you'll get u dabba v by dabba x minus v dabba u by dabba x equal to 0 from this, and u dabba v by dabba y minus v dabba u by dabba y equal to 0 from this. Okay, and from now on you need to do some clever manipulations. Okay, so these are all based on trial and errors. Okay, so what I've done is I've multiplied the first equation by v and I've multiplied the second equation by u. So far I have not used any Cauchy-Riemann equations. Okay, as far as this is concerned, let me use it in this equation. Okay, what I've done is in the second equation I've replaced dabba v by dabba y by dabba u by dabba x. Okay, and dabba u by dabba y with this negative sign by dabba v by dabba x. So at this stage we have used Cauchy-Riemann equations. Alright, in our previous example, what we did was we just eliminated the partial derivatives containing v. Okay, but now we are not doing that. What we are doing is we have eliminated partial derivatives with respect to y. Okay, you may see it here, xx, xx. Okay, I mean, this is how some things work. Okay, fine. So we have now done two things. We have simultaneously applied the Cauchy-Riemann equations and we have multiplied the equations by v and u respectively. Okay, now what we get is this. From the first equation, okay, when you multiply it by v, you will get u v dabba v by dabba x minus v squared dabba u by dabba x equal to 0. And from the second, what you get is u squared dabba u by dabba x plus u v dabba u by dabba x equal to 0, and we are now required to subtract. Okay, subtract the second equation from the first. Okay, well, or you can do the other way. I think I have done that. Okay, so u squared plus v squared times dabba u by dabba x. Okay, and then these two terms will go because they share the same sign. Oh, sorry, same magnitude but opposite. Oh yeah, same sign, but you are subtracting, so that will give you 0. So this proves that dabba u by dabba x is 0, isn't it? Because u squared plus v squared can't be 0. If at all it is 0, then the problem gets solved directly. Okay, so u isn't a function of x. Similarly, you can prove that dabba u by dabba y is 0. Okay, but we'll not go into that. First, by the Cauchy-Riemann equation, if dabba u by dabba x is 0, we can say that dabba v by dabba y is 0 too. Yes, so v isn't a function of y. So 50% of the job is done now. Okay, now we need to prove that u can't be a function of y and v can't be a function of x. Okay, and if we prove that u is not a function of y and v isn't a function of x, it will get proved that u and v are constants, meaning f of z is a constant function. So you can now find a way to prove that. Okay, that dabba u by dabba y is 0 too. It is enough to prove that this is 0 or the other partial derivative is 0, and the rest will follow from the Cauchy-Riemann equations. Now the last topic that we will discuss today is harmonic functions. Okay, now we have already seen harmonic functions in the context of second order partial derivatives. Okay, in particular we said the following. Okay, suppose we have a function f of x comma y. Okay, and if this function satisfies the equation second derivative of f with respect to x plus second derivative of the function with respect to y, if addition of these two derivatives is 0, we called that function as harmonic. Okay, from the theory of partial differentiation. Okay, now it appears that harmonic functions and analytic functions, they have some connection. Let's find out. Okay, and that connection is as follows. Suppose we have the function of a complex variable now, a single complex variable z. If it is u plus iv, okay, and if it is known, excuse me, okay, if we have a function of a single complex variable z in the usual notations u plus iv, and if it is known that this function is analytic, then both u and v are harmonic functions. Okay, which means uxx plus uyy is 0 and vxx plus vyy is also 0. Okay, so if you know that the function is analytic, you have two examples of harmonic functions. Okay, the real part of w is also harmonic, imaginary part of w is also harmonic. Okay, and we call them to be harmonic conjugates of each other. Okay, and precisely what harmonic functions are? Harmonic functions are solutions to the Laplace's equation. Okay, the standard form of Laplace's equation is del squared f equal to 0. Okay, meaning, well, now this del squared is a scalar differential operator. It has dabba 2 by dabba x squared, dabba 2 by dabba y squared, and for us these two operators are enough, but in vector calculus you also have dabba 2 by dabba z squared. Okay, this is the usual definition of del squared, which is also known as Laplacian, just like we have Jacobian or Hessian or Wronskian. Okay, however, at this stage we will not consider this because we are using z for a specific purpose, and we also don't have functions of three independent variables. Okay, now the theory of Laplace's equation and its solutions is called as potential theory. Okay, so to summarize, if the function is analytic, the real part of the function u and the imaginary part of the function v both are harmonic functions. Okay, now we will solve some problems on this. Show that the function u, which is x to the power 4 minus 6 x squared y squared plus y to the power 4, is harmonic, and thus find the analytic function f of z equal to u plus iv. Okay, now what we need to show here is first part shouldn't be a big deal. Okay, what we need to show is that u satisfies the Laplace's equation. Okay, that part is easy. But from this, okay, what we are required to find is the imaginary part of the function whose real part is u. Okay, so the second part is trickier than the first one, but nonetheless we will start by showing that u is harmonic. Okay, write down what u is. It is x to the power 4 minus 6 x squared y squared plus y to the power 4. Find its partial derivative with respect to x. 4x cube minus 12x y squared plus 0. Repeat the process. Okay, find second derivative of u with respect to x. 12x squared minus 12y squared. Okay, now find the partial derivatives of u with respect to y. Okay, 0 minus 12x squared y plus 4y cube. Yes, and then find the derivative of this with respect to y again. So it is minus 12x squared plus our derivative of 4y cube is going to be 12y squared. Okay, add them. Plus 12 minus 12 minus 12 plus 12. So uxx plus uyy is 0, which implies that u is harmonic. And now our job is to generate or to find the analytic function whose real part is this. Okay, now because we know that the function is analytic, we can take the help of Cauchy-Riemann equations. Okay, fine, so let's do that now. Part 2. Because the function is analytic, can we say that dabba u by dabba x must be equal to dabba v by dabba y? Of course, which means we can now get v by integrating partial derivative of u with respect to x with respect to y. Okay, so that's exactly what I've done. Okay, I have gone back to ux, which is 4x cubed minus 12xy squared, and I have put it here as the integrand, which should be integrated with respect to y. Okay, so integrate 4x cube with respect to y. Don't write x to the power 4, okay, because we are not integrating with respect to x, we are integrating with respect to y. So 4x cube y minus, keep 12x as they are, integral of y squared is y cube by 3, so that will make it minus 4xy cube. Okay, let's not ignore a possibility of a function which consists of only x, because we are integrating with respect to y. So this is an arbitrary function at this stage plus constant of integration c1. Okay, now we also have the second Cauchy-Riemann equation, dabba u by dabba y equal to minus dabba v by dabba x. Yes, do we know dabba u by dabba y? Yes, so to find dabba u by dabba x, what we'll do is we'll equate simply the two, and to find v from this, we will integrate negative of the derivative of u with respect to y with respect to x. Now do we know dabba u by dabba y? Of course we know that. Okay, it is present here, negative 12x squared y plus 4y cube. Put it here, but change its sign, okay, because of this negative sign here. So 12x squared y will acquire a positive sign and plus 4y cube will acquire negative sign. Okay, integrate this with respect to x now. So x squared's derivative x cube by 3, so that will make it 4x cube y, and you have to keep this as it is. Okay, so minus 4xy cube plus some arbitrary function possibly of y plus c2, constant of integration. Okay, but you cannot have two different definitions for the same function, so we have to take both f1 of x and f2 of y to be identically 0. Okay, so we have got v now as 4x cube y minus 4xy cube. You may take the constant of integration and put it here, but that's okay, fine. So we have successfully obtained v, and now we are going to get back f of z. Okay, now this is important. What we have currently is, we know what u and v are in terms of x and y. Sometimes they ask us to get the function in terms of z. Okay, and to do this, what we do is the following. We take the help of Milne's method. So according to this method, to get f of z in terms of z from x and y, what you have to do is the following. You have to put x at z and you have to put y at 0. That's it. Okay, so let's see what happens. You will now see that except for the first term of u, in each and every term y is present. Okay, so this forces us to define f of z as z to the power 4. And well, this is true because from the binomial theorem, if you expand x plus iy to the power 4, what are you going to get? X to the power 4 plus 4 times x cube times iy, okay, plus 6 times, okay, let me write the real part below x to the power 4, minus 6 because we are going to square iy, x squared y squared, then plus 4 times cube of iy times x, so cube of I is minus I, and then again the fourth power of iy, which is y to the power 4. And this is exactly what we have got as u and v. U is x to the power 4 minus 6 x squared y squared plus y to the power 4. Yes. What is v? Is v not equal to 4x cube y minus 4xy cube? Yes, it is. Don't forget this negative sign. Okay. I mean, we know that any polynomial function is always analytic. Okay. And if you observe carefully, you may get a hint. Okay, this is a homogeneous function of degree 4, but more importantly, look at the coefficients. Okay, look at the coefficients 1, 6 and 1. Okay, so you expect the other thing to have the remaining binomial coefficients of 4CR, right? So which are 4C1 and 4C3 respectively, and you can see them here. Okay, so this is how you typically solve a problem where the function is analytic, it is known, and you have to show that, or you have to find the other part. Okay, if the real part is known, you have to find the imaginary part of the function, and vice versa. Okay, using the Cauchy-Riemann equations and integrating. You may find this similar to the process of finding solutions, or general solution of exact differential equations. Okay, we have done a similar thing there. Okay, fine. We'll solve the next problem now. And yes, in this problem we will make use of both Cartesian as well as polar versions of the Cauchy-Riemann equations. Okay, so in this problem we are given v, we need to find u. Okay, question 2. If v is negative y upon x squared plus y squared, find u such that u plus iv is analytic and determine f of z in terms of z. Okay, fine. Now because u and iv is analytic, we know that both u and v will satisfy the Laplace's equation. Okay, or both are harmonic functions. So you may take it as homework to show that vxx plus vyy equal to 0. Okay. However, now what we will do is we will straight away apply the Cauchy-Riemann equations. Okay, so what do we know? First Cauchy-Riemann equation says partial derivative of u with respect to x must be equal to partial derivative of v with respect to y. Apply the division rule. Okay, derivative of negative y with respect to y, because this is v, is minus 1. So minus 1 times the denominator minus first function as it is into derivative of the second function. Okay, x squared's derivative 0, y squared's derivative 2y divided by the square of the denominator. Okay, simplify. First term minus x squared minus y squared, second term plus 2y squared. So this is how you will get da by u by da by x. Okay, fine. Now the problem is this. If we decide to integrate our function with respect to x, in order to get u, the integrand will be y squared minus x squared upon x squared plus y squared raised to 2, which is a difficult integral, right? Therefore, what we'll do is we'll try to apply the second Cauchy-Riemann equation now. Okay, these equations will only help us till the integration. Okay, after that it's up to us, okay, whether we can integrate it in terms of the known functions. Okay, fine. So we have to now stop here as far as the first Cauchy-Riemann equation is concerned. So let us try whether the second equation is of any help. Has to be, right? Okay. So here we will recall the second Cauchy-Riemann equation, which says dabba u by dabba y is minus dabba v by dabba x. Okay, fine. See, now because the numerator of v doesn't contain x, it is easier to differentiate it with respect to x now, right? Okay, keep the numerator as it is. We have 1 upon x, I mean a function equivalent to 1 upon x, so its derivative will be minus 1 upon x squared. Okay, this negative sign has come because it is present in the equation itself, Cauchy-Riemann equation. This negative sign has come because it is present in the formula of the derivative of 1 upon x. Okay, and don't forget to multiply it by the derivative of the inner function with respect to x. Okay, we have eventually 3 negative signs, so you have to write it here, minus 2xy upon x squared plus y squared squared. Okay, so this is dabba u by dabba y now. All right, so we may now consider this as our integrand and start integrating it with respect to y. All right, so if we are integrating with respect to y, we can take negative 2x common, but only take negative 2x, negative x, sorry, because we will require 2y with dy for the substitution. Okay, so if we substitute x squared plus y squared equal to t, as far as y is concerned, x is a constant, so 2y dy equal to dt. So the function to be integrated will simply be 1 over t square, whose integral is minus 1 upon t, but we already have negative sign here. Okay, so the negative sign won't come here, it will simply be 1 upon x squared plus y squared plus some possible unknown function of x, okay, because we have integrated with respect to y, arbitrary function, plus the constant of integration. Okay, so having obtained u from the second Cauchy-Riemann equation, let's now see whether this function that we have got here as u, does it satisfy what we have here. Okay, dabba u by dabba x. Okay, y squared minus x squared upon x squared plus y squared raised to 2. And see, this is to check whether f of x is present or it is 0 throughout. Okay, so differentiate u with respect to x. Simply stated, apply the division rule on x upon x squared plus y squared. Derivative of first is 1, second function as it is, minus first function as it is into derivative of second with respect to x, so just 2x. Okay, divided by square of the denominator. Yeah, okay, I should have written plus f prime x here. And derivative of constant is anyway 0. Okay, now simplify the numerator, you will get y squared minus 2x squared, okay, plus f prime x equal to plus 0. Okay, derivative of constant. Now if you observe carefully, there is no term in dabba u by dabba x which only consists of x. Dabba u by dabba x is y squared minus x squared upon x squared plus y squared raised to 2, which means f prime x is 0, so f of x is, I mean, doesn't involve x in its definition. Okay, so this confirms that u is equal to this, the function that we have got, x upon x squared plus y squared plus the constant of integration c. Okay, now we have got w. Okay, if we drop c, okay, then we will get x upon x squared plus y squared plus I into minus y upon x squared plus y squared. This was given in the problem itself. Okay, so this is mod of z upon mod of well, it is z bar upon mod of z squared, and I think it is also 1 upon z. Is it? Yeah, it is 1 upon z. Okay, you can check it by multiplying it by the complex conjugate. Okay, 1 upon x plus iy into x minus iy upon x minus i. Yes, it is complex conjugate. Oh, it is 1 upon z. Okay, mod z up, sorry, z bar upon mod z square. Okay, now the Cartesian equations have taken us considerable amount of time to solve the problem, but we can also solve it by polar equations. Okay, so when you solve by using polar form, always look for presence of terms like x squared plus y squared. If this is present, then it is an indicator that using polar forms might prove to be a better decision, okay, or a good decision. All right, so to get this in the polar form, we will first convert v into, or as a function of r and theta. Y is r sin theta, x squared plus y squared is r squared, cancel r, so v will be negative sin theta upon r. Okay, now recall the Cauchy-Riemann equations. Okay, first differentiate v with respect to r, so dabba v by dabba r will be sin theta upon r squared, and dabba v by dabba theta will be minus cos theta upon r. Okay, now you recall the equation that dabba u by dabba r is 1 upon r dabba v by dabba theta. Okay, the first Cauchy-Riemann equation in the polar form. So this actually is saying that dabba u by dabba r is minus cos theta upon r squared. So you can now get u by integrating this function with respect to r, which is cos theta upon r. Okay, because integral of negative 1 upon r squared is 1 upon r. You may consider a possibility of an arbitrary function not involving r but involving theta plus the constant of integration. Let's call it C2. Okay, now use the second Cauchy-Riemann equation, okay, which says dabba v by dabba r is minus 1 upon r dabba u by dabba theta. Okay, so minus 1 upon r dabba u by dabba theta is sin theta upon r squared. Shift minus 1 upon r to the other side, so dabba u by dabba theta will be minus sin theta upon r, right? So integrate this with respect to theta now to get u. Okay, so what will it be? It is going to be integral of minus sin theta with respect to theta, so cos, keep r as it is, plus some possibly present function of r, call it f of r, plus the constant of integration c1. Okay, now having obtained everything in terms of r and theta, let's convert it to Cartesian form. Multiply by r, divide by r cos theta x, and r squared is x squared plus y squared. So we have got the same answer through the application of Cauchy-Riemann equations in the polar form, x upon x squared plus y squared.